as successive approximations the terms that we have confined. Now, if you do that systematically, what happens with the small editors ends up by being a resonance chiral Lagrangian with just three states, vector, axial, and a scalar, which is very reminiscent of resonance chiral Lagrangian models which were worked out at the phenomenological level earlier. So in that respect, you can see that these resonance chiral Lagrangians with a finite number of states can be viewed as a simplified version of a large in CQCD when you limit yourself to just a few states. Now, before I go into more details, let me tell you two observations which I think are crucial, which were crucial, at least to me, in the evolution of all those ideas, which has one of them is the fact that if you look at the couplings of the effective chiral Lagrangian of the strong interactions, you can actually prove, and that's totally rigorous, that they are nothing else but the coefficients of the Taylor expansion of appropriate Green's functions that you construct with local operators. Well, now, the reason why the effective chiral Lagrangian of the electroweak hadronic interactions is a much more complicated thing, which is the subject Chimo was working on, is that, in fact, you can also prove rigorously that the couplings of this effective coupling Lagrangian of electroweak interactions, in order to compute those couplings, you have to do integrals of appropriate QCD Green's functions, integrals over external momenta. Most of them, they only involve 2-point functions with a finite number of local operator insertions. And then, therefore, you have the problem of matching long and short distances. In most of the cases, there is something that you already know about this, which has, from integrating the heavy degrees of freedom, W's, and heavy quarks, you have a Lagrangian, which is 4 quark operators, like 4 quark operators, and this at short distances has been done using perturbation theory. But then in order to go down to the couplings of the Lagrangian, you still have to do an integral, and you have to match exactly the behavior of short distances. That has been, well, that's one of the difficult problems in the game. Now, little by little, we realize that one of the drawbacks of these models, like the Manuel-Georgi model, the standing and William-Alcino models, is that they don't have this matching to short distance. So little by little, this was replaced, at least for some of us, with a more direct approach, where in fact just pick up the relevant Green's functions that you have in a model, that you have in order to compute some coupling, and then simply make an ansatz for this Green's function of a finite number of states, make sure that you adjust the short distance properties given by the operator product expansion by attuning the masses and the couplings, and the long distance behavior that you already know from the chiral Lagrangian of the strong interactions. If you satisfy these two constraints, then you are perhaps in a good shape to do calculations. Now, this is something which has been done by many people who have participated to that, not exactly with the same approach. There are variations on the same theme, like there are variations on a theme in music. There are discussions on what is the best variation and so on. But the ideas, I think, behind all that are the ones that I have indicated here. And Chimo, of course, participated a lot, especially with in collaborations with Tony and in collaborations with Hans in many of these calculations. Now, so far for the historical development of that, there are still two, in my opinion, two basic problems in these developments. One has to do with the fact that in spite of all our efforts, in spite of the beautiful results that sometimes we have got, the problem is that we have still a finite number. We are working with approximations with a finite number of narrow states, whereas large C is an infinite number of narrow states. Now, the differences going from finite to an infinite number of states can be considerably, and people, especially Santi and his collaborators and Tony and his collaborators have been working on these differences of going from a finite to an infinite number of states. Another more sort of difficulty that one can see is that this thing, when you try to implement this approach, even with a finite number of states, things become very complicated when you try to do corrections, let's say, to the chiral limit. You have to work with several grid functions. You have to work out the operator of product expansion with insertions, and that becomes a very, very heavy and complicated thing. So I've always been trying to think, couldn't we have some kind of approach will be simple, which will not be reliable to get numbers to a few percent, but should be reliable to get orders of magnitude, so that if we produce more sophisticated models, we can confront with the sort of order of magnitude estimate and try to see whether we agree or we disagree, so that we get some orientation in all that. And that's exactly what I would have liked to tell Chimo and to tell him why I was getting interested again in the constituent quark model. Now, let me get to the point about this model in a more technical way. The idea of the model, actually, which I forgot to say, is that the idea of Manohar and Georgia was that if you integrate degrees of freedom in QCD, you may get to an intermediate stage where, in fact, the spontaneous chiral symmetry breaking has already taken place at a given scale, but that scale may be different to the scale of confinement. So you have a gap between the two scales in which an effective description, not yet in terms of hadrons, but in terms of constituent quarks and pions, the lowest term of the Lagrangian, may be already a good approximation. That was the idea, and that's what the Lagrangian that I have written here reflects. The terms which I have underlined are the Manohar-Georgi terms. The idea is that you have just this term explicitly in the pion, so that will become a constant you have to live with. That will be also a constant, I will come to that later, which you have to live. And of course, there is a constituent mass because you have had a spontaneous chiral symmetry breaking. There are still gluons. That was one of the basic assumptions of their model, because the gluons, in a way, were necessary to explain some of the spectroscopic successes of the model. However, they assumed that the coupling constant of the gluons is not longer running. It's just fixed to a given scale. Roughly, it's 0.35 or so. So typically the scale of 1 GeV. Now, you may ask me why you have all these extra terms. Well, first, let me tell you a little bit more for those of you who are familiar with those things, and if you are not familiar, just forget about it. This is the definition. The quark fields, let me see how I'm going to. The quark fields are not quite the quark fields of the QCD Lagrangian. They are rotated quark fields. That's to say, physically, you have amputated from those quarks the Goldstone particles by a rotation. This is what I have here. And that's why I call them big Q, capital Q instead of small q. And also, these people didn't have external sources, so I put this with external left, right sources, vector sources, and also scalar, pseudo-scalar sources, which I have frozen down to the Lie quark mass cells. This is the mass matrix of the quarks up, down, and strange. So the notation is here. And now I'll tell you in a minute why I have these extra terms. This C, L5, and L8. This has to do with a remark that comes from this paper by Weinberg, which is now published in Physical Review Letters. In fact, recently Weinberg made the following observation. He said, in the large density limit, the Lagrangian of the constituent chiral quark model is renormalizable. There is a second claim, which is even more stronger, which is that this Lagrangian is the effective Lagrangian of large CQCD at low energies. Now, the first remark, the first observation is rather trivial. If you think 5 minutes, you convince yourself that that's right. It has to do with power counting and so on. And that's a nice remark. I didn't think of that, and perhaps people here thought about that. But it's trivial. It's one of these trivial remarks that when somebody makes it, you say, "Oh, yes, of course. How come I didn't notice that?" I think Chimo would have liked that. The claim is incorrect, and I can tell you why it's incorrect for many reasons, but let me skip that. Now, looking back to the Lagrangian I wrote before, I can tell you that, in fact, it turns out that in the limit where you put this coupling, this axial coupling to 1, this constituent chiral quark Lagrangian has very nice features, and I would like to discuss with you the good features. I'll also tell you the bad features. Now, the good feature is that if you integrate, the idea of the Lagrangian is you have this approximate Lagrangian at the intermediate scales. If you integrate the heavy quarks, you should get the specific Lagrangian of the Goldstone modes. So what do you get for the couplings? Now, this was known for a long time. And in fact, in that paper with Priu and Josette Daron, we already realized that some of the couplings of the Gasserlot-Wheeler Lagrangian, when you compute them with SGA equals 1, they come finite. And they are not so bad compared to the phenomenological determinations. However, if you left GA different to 1, they all become logarithmically divergent. So that's why I like to have J equals 1, because if you leave J equals 1, since those are finite, you don't need to put those as counter terms. And in fact, the only counter terms that you need to put are the ones that I have put here. That's to say L5 and L8, which doesn't matter what you do, they will come divergent. And therefore, those you have to put them as counter terms. Also, it's well known that the pi plus pi zero mass difference in the constituent chiral quark model comes infinite if you take it seriously, because there